record, and then let me hide this thing. Okay, so as we discussed about the exam, so all the questions will be related to the slides. So you can just go through the slides. If you understand everything in the slides, you should be absolutely okay with the midterm exam. So today I'm going to help you to go through some questions to remind or refresh your mind to try to remember what we have learned. And you can use similar strategies after this class to review every slide to get better idea about what we have learned. So in the first chapter, we have learned the basic ideas about charges and electrostatic forces. So let's go through some of the questions. I'm not going to go through all the questions for each slide, but at least let's go through some of them. So first of all, what's the unit of charge? Do you still remember? Okay, should be Coulomb. And please also keep it in mind, Coulomb is a very big unit. So usually we use nanocoulomb, millicoulomb, something like that. Very small, not very small, normal unit. Now a charge alters the space around it. What is the alteration of space called? Great. So see, so these are the conceptual questions. So we will have some conceptual questions because as I said, the conceptual questions in my mind is more important. We have to include some calculations. Otherwise, if there's no any calculations, it doesn't feel like a physics course or math related course. But in my mind, so let's say 10 years later after the class, you might not remember how to do the calculations. You might forget the equations, but those conceptual questions, the definitions, the ideas, that's the most important thing. It will be always in your mind if you understand it, not just by remembering it. So it's better to understand it. Once you understand it, it will always be in your mind. But if you just try to remember it, you may forget it. So one basic idea is the electrostatic field or electric field. And then if a negative charge, the rod is held near a neutral metal ball, the ball is attracted to the rod. Which option? Right. This is also a basic idea in our slides and also in the textbook. So which one is right? So once you have, this is the way to measure, define or measure the electric field. If you remember, now if you have charge, might be positive, might be negative. Let's say a positive charge. If you want to measure the electric field, you need a probe here to see what's the direction, what's the strength of the electrostatic force, so that you can define or measure the electric field. This is very simple because you only have one charges, but let's say if you have several charges, now what's the direction and strength of the electric field at this position? It's difficult to know if you have a lot of charges, or they might not be even point charges. There could be some materials that has a charge distribution. Then it's difficult to calculate. So the way to measure it is just put a probe and see what's the direction and the strength of the electric field. Okay. So first of all, this is related to the charge examples in our in our lectures. Do you still remember what is the charge on the glass rod and what's the charge on the plastic rod? Let's say if you use silk to rub the glass and you use wool to rub plastic rods, then what's the charge on glass and what's the charge on plastic rods? It's positive on glass and plastic on negative on plastic. But that's a very classical example. It doesn't mean glass always have positive charge. It only happens when you use silk and glass to do the rubbing process, and then the glass will have the positive charge. And when you use wool to rub the plastic rod has negative charges. And now let's go back to this question. So which option? D. Still D. So first of all, charge the glass doesn't mean a positive charge glass. In our lecture, please keep it in mind. In our lecture, the glass is positive simply because you obviously use silk and glass. When they are used, the glass is wearing positive and the silk is wearing negative. But here it only says glass. It doesn't say it's rubbed by a silk. So the glass rod could be positive, could be negative. This is one thing. Another thing, let's say even I told you the glass is positive and the plastic is negative rod, still it's difficult to tell because object attract the glass rod. Does it mean the object is negative? Still, it's difficult to tell because if you remember, the charged rod can pick up neutral small pieces. If it's a neutral, it might also have attractions to the charged atom. So, so this is number 2 reason. So totally in this question, there's no enough information to make your judgment. So a rod attracted a positive charge and bound the rod is. So if this is positive and it's attractive to a rod, The rod could be negative, of course, and it can also be neutral. As we learned, the charged object can be attracted to a neutral thing because of the induced charge. When you have a neutral thing, there is a charge here. The neutral object will redistribute its charges. So it has some negative charges at this end and positive charge on the other end. Do you remember that? That's induced charge, so that the so that the positive charge can attract the neutral object. Okay, what about this question? Again, this is something related to induced charge. Once you have positive charges here, then the charges on object 1 and 2 will be redistributed. Okay, so what is your choice? Right, so induce the charge. Once you have positive thing here, the neutral object will have negative charges close to the object, and then the positive charges will be repelled to the other end. And these two spheres are metal. That means the charges are free to move, and they're touching each other. So the charges are free to move from one object to the other object. So finally, the final distribution will be negative here and positive there. Let me see. Oh, so there's a B step. Okay, so okay, there's one more step. So first of all, if you put the rod here, you have negative charges here, positive charges here. However, there is a step B happened, which is removing the rod away. When you move it away, the entire system becomes neutral again. So it will be neutral and neutral. And then you separate the two spheres. So both of them are neutral. But in our exam, it could be different. Let's say if you don't have step B, what happens? If you put the rod here, and then with the rod here, you move away the sphere 2, then what happens? It will be C, right? So it's my mistake. I didn't read carefully about the step, the process, but in your exam, please read it carefully. I may have different steps or process compared to the slide. Okay. What about in this situation? So first brought near and then separate and then move the rod. Yeah, this time it's C. Okay, what about this question? So this is metal. In previous example, we said it's a metal. If it's a metal, what happens? So it's difficult to tell. So for most of the metals, the the electrons are kind of free. It's more flexible than the protons. But in this example, we don't get any conclusion if the protons are fixed or not. So there might be some, let's say, electrons moving. Meanwhile, there might be also some other atoms or protons moving in the material. Okay, what about this one? Okay, let's do it together. So first of all, first step, P and Q are touched and they're metal. So first keep in mind they're metal. Metal have free charges. So if you touch P and Q, what happens? The charge redistributed and the net charge for the whole system of P and Q should be 2. And the charges should be evenly distributed to those two spheres. So totally you get +2, and each of them have +1. +1 here and +1 there. And now next step, separate them. Separate them, you get +1 on P, +1 on Q. And then touch Q and R, then redistribute the charge, it's get neutralized. So the answer should be 0. But keep in mind, in our exams, the numbers could be completely different. So you need to understand, not just remember the numbers. Okay, what about this one? Now you see the force 1 on 2. What is the force of 2 on 1? Which option is right? So you may have learned Newton's laws. Have you learned Newton's laws before? What is Newton's third law? Hmm? What's the first law? Newton's first law? Have you learned Newton's laws before? No? Exactly. So the third law tells us there's no single force. If there is a force happens, there must be a pair of force. The force should be a pair of A on B and B on A. That's action and reaction. And those two forces should be in the same magnitude but opposite direction. So the force of A on B should be equal to B on A, but in opposite direction. This is Newton's third law. Another classical question is, there is a mosquito hidden by a truck. So which force is greater? Number one, the force generated from the truck on mosquito. Number two, the force from mosquito to the truck. Which one is stronger? It's the same. That's action and the reaction. The truck hits the mosquito at the same time hits the truck. The force is very small, actually. But for mosquito, it's fatal. But for truck, it's nothing. Because truck is strong. It's big. So the same thing here. Okay, what about this one? So the key is Coulomb's law. You remember Coulomb's law? To calculate the force, you need Q1, Q2 over R squared by a constant. So when R is half, then the force should be four times. Okay, this one, which is the direction? So here we're only talking about the direction. So it's B. What about this one? So plus Q generate the force in this direction, minus Q generate the force in that direction. This force plus that force, you get D. What about this one? So negative Q generate the force of repelling, and plus Q generate the force of attraction. Which one is bigger? the repelling force is bigger because they're getting closer. So the net force should be B. Okay, which one is stronger? Why? Okay, so it's a closer. What about in this case? You have A and you have B here. So which one get stronger electric force or electric field? Why? It's the distribution of the field lines are denser, so you get A here to have to be stronger electric field. What is the unit of unit vector? B. So unit vector doesn't have unit. It simply just tell you the direction. There's no unit for a unit vector. So which is the electric field at this position?
Can I ask you a question first? On the unit vector, how do you know if it's negative or positive? Which was is just the R hat?
Oh, let's say, let's make some simple examples about unit vectors. Usually we have X and Y in Cartesian coordinates, let's say in two-dimensional cases. If we define a unit vector, which is R, it's in X direction. Then let's say if you have a vector which is 3 times R is the unit vector, then you immediately know the magnitude of this vector is 3. The direction is defined to be along the unit vector. But if it's negative 3, that means magnitude is 3, but the direction is against the unit vector. So negative or positive simply means you follow the direction or against the direction of the unit vector. So which is the electric field? That's very simple. Okay. That's all for chapter 22. Now let's see chapter 23. So it's very similar to previous questions. And this is too easy for you. We already talked about that. Okay. So let's see this example. When R is much, much greater than B, then what's the strength? When R is very far away from those three charges, you can consider the three charges to be. Thank you. You can consider it to be a single charge if the distance is very, very far away. You can consider it to be 4Q. Then what's the electric field strength? Simply C. You just consider all the charges to be a point charge because you're too far away to distinguish the very small distances between those three charges. So similar to the electric field strength, another way to ask is which has stronger acceleration. So which one has stronger acceleration? A, because the field lines are denser. So what's the answer for this question? So you have positive charge generating field line in this direction, the negative charge generates field line in that direction. So totally you will have, oh, sorry. So this is the electron. Electron means this is negative. So the positive charge will generate, let me erase everything. So the positive charge will generate an electric field in that direction and negative generate a charge in this direction. So when you combine them two, you get A. So what's the charge density? So what's the length of the wire? The total length should be 4. And then the total charge is 8 nanocoulomb. 8 nanocoulomb over 0.04 meters because it's in centimeter. So when you do the calculation, you will get the final answer. In our exam, please keep in mind the numbers might be completely different. You need to know how to calculate. So a flat circular ring is made from thin metal, which is shown here. Charge is uniformly distributed when, let's say, when the ring is very thin compared to the radius, then the charge density. How do the charge density? Again, Q over the length. And the length is 2 pi r, right? Circle length. So, oh, okay. It has two sides. Let's see. Very thin metal. Okay. So the surface charge density. I see. So it's asking the surface charge density, and if it considers it has two sides, then use Q over 2 pi r, and then also it should be over, let's say 2r, 2W. Because we're not asking for the density, the wire density. It's a surface density. So we need to first calculate the surface. So the surface should be 2 pi r then times w. That's the length times width. You get the area, but you have two sides, then times 2. That's the total area. Okay, and then you use the total charge over it, get the answer. Okay, it's a very, you need to read the problem very carefully. I missed the surface charge density. So if I solve the problem, I may get a wrong answer. So which one has higher acceleration when two charges are putting on the surface charge? And it's an infinite plane of positive charge. Which one has stronger acceleration? Are they the same? Same. So do you remember the way to calculate the electric field for infinite plane of charges? So first of all, what's the direction of the field lines? Is it something like that? Is that right? No. If that's infinite large charge the plane, the field lines should be perpendicular to the plane. Do you remember that? It's always perpendicular to the plane. And when they're parallel, when the field lines are parallel, then the dense of the field lines are same at here or there or there or there because they're parallel. So the density of field lines are the same. So the strength of the electric field should be the same. And the force should be the same. That's why when we calculate the electric field, do you still remember the equation? Electric field for infinitely large plane. It should be a constant times the charge density let's say if we define it to be eta or sigma or something over the epsilon. So it's independent from the distance between the point and the plane. So here, which position has the strongest electric field? Which one? C. Again, parallel field lines means the strength is the same at any position. So which direction is the velocity? Which one? So C is right. But in this example, if you choose B, I'll also give you. It's difficult to say what is short time. So, and we don't know how strong is the electric field, but we know it should go to the direction of upper right. So this is the positive charge, and then it goes in this direction. So what's the electric field? So let's say at this point, its velocity is here, and then the velocity has changed to be in this direction. The difference between them is C, because you can tell there's always a force pushing it to the right so that it makes turns in this way. Which one has no force? C, because only in C, the negative part get a force down, the positive part get a force up, and they're against each other. In all the other cases, it's going up, here it's going down, it has a torque. But here, are we asking net force or net torque? We're asking net force. So let's say in case of A, you have a torque, but what is the net force? Still, the net force is 0. So in all cases, you have 0 net forces. Please pay attention to the question. If we ask which one has no torque, then the answer is C. But which one has no net force? All of them. So which one has no torque? Right. Okay, done for chapter 23. Now, last chapter. Gauss law. In Gauss law, we have to do some calculations. So get prepared to do calculations for exams using Gauss law. So the amount of electric field passing through the surface is called what? A. That's flux. That's the definition of electric flux. Gauss law is useful for calculating electric field that are symmetric. We have mentioned it a lot of times. So for those who have other classes and if you need to leave, you can just go. We'll keep it in a video and I'll upload it to the YouTube. Yeah. So Gauss law applies to what? Close the surface. The electric field inside the conductor in electrostatic equilibrium is what? 0. The electric flux through the shade surface is So the flux equals to E dot product A. In this example, E and A are in the same direction. So it becomes just E times A without the vector product. So you will get answer to be C. What about in this case? A, because there's no field lines going through it. There are only field lines going along it, either over it or below it. So flux is 0. What about in this case? Great. So here, surface A and B have the same shape, and which one has a larger flux? The answer is A, because there are some field lines going through A, but not going through B. But for all the field lines which go through B, it has to go through A. So A has more field lines going through it, which is flux. So which surface has a larger electric flux, A or B? They're equal, because any field lines going through A must go through B. So which one has 0 electric flux? Only A, because here in this case it has 20 going out, 10 going, 30 going out. But in this case it has 20 going in and 30 going in. Okay. Okay. Positive or negative? Now let's count. So how many of them are going in? This is in, this is in, this is in. So for field lines going in, it's 15 plus 15, 30, 30 plus 20, it's 50. 50 in. Let's see how many field lines going out. 20 plus 10, it's 45. So there are more field lines going in. That means there's a negative charge. So the answer is wrong. It should be inward rather than outward. I think there might be an arrow wrong or something. Yeah. But in our exams, we will make it right. So which one has larger electric flux? That's Gauss law. If you remember the flux, there are two ways to calculating flux. One is an integral of E dot product dA. In this case, it's difficult. Another way is using Q over epsilon, right? Times a constant. Let's do not care about constant. Which one has greater Q? It will have greater flux. So the answer should be B, because it has greater Q. Now another question might be, now you have surface C here, D here. If you compare B, C, D, which one has greater flux? They're the same because the net charge inside them is the same. Which one is right? They should be the same because the charges are the same. Q over epsilon equals to E A. A is the area, the area. Area is the same, so E should be the same. What about this example? So the answer should be B. The field line should be something like that.
Flux can be zero then?
The flux must be zero. Yeah, if the charges are the same. And what about this example? Okay, so first of all, let's talk about this. Let's call it this is surface one. This is surface two. For surface one, it contains. Oh, the label is wrong. So this should be Q1. This should be Q2. For surface one, it contains Q1 and Q2. For surface two, it contains only Q2. Q1, sorry, only Q1. Q2 is out of the surface. So if you understand this, then let's say here, this is generated by Q1. And here it's generated by Q1 plus Q2. So Q1 plus Q2 equals to Q, and Q1 equals to 2Q. Then this is not a good example because it's misleading which one is Q1 and which one is Q2. But the idea is when you do the calculation, you should know this surface contains only Q1, but the other surface contains Q1 plus Q2. So which one is right? We need to leave the classroom before 3, so we still have a couple of minutes. So what is the answer for this? Now we're asking two flat ends. So the distribution of field lines is something like that. So Are there any field lines going through the flat ends? No. But if we ask the wall, if we ask the flags of the wall, which is here, then you need to calculate the area. So you need to calculate the Q inside this cylinder, because the flags going through the wall are the flags going through the entire Gaussian surface, because no field lines are going through the ends. They're all going through the wall. So Q over epsilon. How to calculate Q? It should be, let's see. Okay, so let's say if we know E, then we should calculate E times A. So how to calculate A? 2 pi L. Then you get 2 pi L A, 2 pi L E. Okay, so we have to leave the classroom, but please try to going through all the questions in the lecture 20. Let's see, what is this lecture? 22, 23, and 24.
Where can we find the slides?
Hmm?
Where can we find the slides?
You never download the slides?
Oh, you just send them to email?
Do you get any